Hello friends, this is Priyanka. Today we are going to solve a problem on loss of head due to sudden enlargement. So these are also considered as the minor losses, and these losses takes place due to change in velocity. So first I will read what is the given problem. At a sudden enlargement of water main from 240 mm to 480 mm diameter, the hydraulic gradient rises by 10 mm. Estimate the rate of flow. So this was the given question. Let us first understand the diagram as per given data. Now it is given that initially the diameter of pipe is 240 mm. So we have to show here the pipe with small cross section. And then it is getting enlarged for this 480 mm. So again we have to show that there is the pipe of diameter 480 mm. So we can say that at inlet there is the section 1 having diameter D1 is equal to 240 mm, which is equal to 0.24 meter, and from that we can calculate the area, as this pipe is having circular cross section. So area A1 is equal to pi by 4 D1 square, that is pi by 4 0.24 square. And then at section 2 we will consider at the outlet with diameter D2 480 mm, that is 0.48 meter. So area A2 is equal to pi by 4 D2 square, that is pi by 4 0.48 square. Now we have to find out what is the rate of flow. That means we have to find out the discharge Q, and we know that what is the formula for this discharge Q, that is A1 V1, or we can also say A2 V2. So now area A1 and A2 are known. So we have to find out what is the velocity V1 or V2. So either we have to find out velocity V1 or we have to find out the velocity V2. So now if we observe, there is the rise of hydraulic gradient is also given. So what is this hydraulic gradient? So it is the pressure head plus datum head at section 2 minus pressure head plus datum head at section 1. So what is the pressure head? That is P2 by rho g plus Z2 minus pressure head plus datum head at section 1, that is P1 by rho g plus Z1. So we have to take here the bracket. So this is the bunch for this pressure head plus datum head at 2 minus this is again the pressure head plus datum head at 1. So we have to make the bracket, and it is given in millimeter. So what is the standard unit? Meter. So again we have to take 10 millimeter, that is equal to 1 by 100 meter. So now we will consider the rate of flow, that is Q, that we have to find out. So for that, if we apply Bernoulli's equation at section 1 and section 2, then here the pipe is getting enlarged. So there is the losses due to sudden enlargement. So while applying Bernoulli's equation, we have to take into consideration this minor loss due to sudden enlargement. So what is the Bernoulli's equation? That is P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2 plus He. Now what is the formula for this He? So these sudden enlargement losses, these are considered as the minor losses, and these are due to the change in velocity. So here He is equal to V1 minus V2 bracket square by 2g. So again we don't know V1 and V2. So we will convert this V1 in terms of V2, or we will convert this V2, value of V2 in terms of V1. So we will apply again the continuity equation at section 1 and 2. So we know that A1 V1 is equal to A2 V2 by continuity equation. So if I take this equation, then V1 is equal to A2 by A1 into V2. So what is A2, what is A1? So here pi by 4 0.48 square, pi by 4 0.24 square. So if I take here this pi by 4 is getting cancelled, and this D2 by D1 whole square. So I will write here 0.48 by 0.24 square into V2. So here if I simplify this, so here I will get that is 2. So what is the 2 square? That is 4v2. So I will get here v1 is equal to 4v2. So I will make the bracket. Now I have get what is the value of v1? That is v1 is equal to 4 times v2. So now if I observe this HE, that is the head loss due to sudden enlargement, I will put here the value of V1, that is 4V2 minus V2. So what is the 4V2 minus V2? That is 3V2 bracket square divided by 2G. So 3V2 bracket square, that is 3 square is 9. So 9V2 square by 2G. So I can directly use this HE is equal to in terms of V2, that is HE is equal to 9V2 square by 2G. So in this Bernoulli's equation, I will take HE in terms of V2. Now we will rewrite the Bernoulli's equation in terms of rise of hydraulic gradient and in terms of V2. So we have to take the value of V1 in terms of V2. So how we can rewrite this equation? So if we observe here P2 by rho g plus Z2 minus P1 by rho g plus Z1, which is equal to 1 by 100 meter. So if we observe here P2 by rho g plus Z2, we have to take on the right hand side as it is, and we have to shift this P1 by rho g plus Z1 towards this right hand side. So here if we observe right hand side will become the value for the rise of hydraulic gradient. Then the remaining terms, that is V2 square by 2G and HE, in that is the formula for HE in terms of V2, that we have to shift towards the left hand side. And this V1 also we have to write in terms of V2. So what is V1? That is 4V2 bracket square by 2G minus, now this V2 square by 2G. So we have, if we shift here, this plus sign will become minus V2 square by 2G. And then this HE, so what is the value of HE? It will become minus HE, that is minus 9V2 square by 2G, which is equal to, on right hand side, here this we have to take the value of 1 by 100. So again if we simplify this left hand side, then this denominator 2G is common. So what is the value of 4V2 bracket square? That is 16V2 square minus V2 square. That is 15V2 square, and 15V2 square minus 9V2 square, that is 6V2 square. So 6V2 square by 2G is equal to 1 by 100. So V2 square is equal to, we have to shift all the terms to the right hand side. So 2 into 9.81 divided by 6 into 100. So what is the value of V2? We have to take the square root and it is equal to 0.1808 meter per second. So now it is easy for us to calculate the discharge because V2 is known and A2 that we already know. So A2 here we have to take this value multiplied by V2, so which is equal to 0.03275 meter cube per second. So this meter cube per second we can also convert into liter per second. So how to convert? We have to multiply with 10 raised to 3, that is 32.75 liter per second. So this is the answer.